what's up everybody? Patrick here. Welcome back. Moving on to another test question, another tough test question. So Sam thinks he found a pattern for determining the sum of the reciprocals of any three consecutive numbers. So the reciprocals of any three consecutive numbers. So notice we got 3, 4, 5 consecutive numbers and the reciprocals of them. So 1 over 3 plus 1 over 4 plus 1 over 5 is equal to 47 over 60. Or another example is 1 over 6 plus 1 over 7 plus 1 over 8 is equal to 146 over 336. Now this fraction actually simplifies, but the next sentence describes this pattern. So this is before simplification. So what he concludes is that the numerator of the sum is 3 times the product of the first and third denominator plus 2. And also the denominator is the product of all three denominators. Is he correct? Okay, so let's first see if he's correct with these specific examples, and then let's try a general case and see if he's going to be correct for all numbers. So we got 1 over 3 plus 1 over 4 plus 1 over 5. So this numerator, 47, he concludes is the sum, or it's the, sorry, I'm getting confused here. The numerator of the sum is 3 times the product of the first and third denominator plus 2. Well, 3 times the product of the first and third denominator. So the product of the first and third denominator is 3 times 5 plus 2. Notice when we do this, this would be 15. 3 times 15 is 45, plus 2 gives us 47. So it seems to work out in this case. And then he says the denominator is the product of all three denominators. So 3 times 4 times 5, what does that give us? That actually gives us 60. So his observation is correct for this example. What about this one? 1 over 6 plus 1 over 7 plus 1 over 8 is equal to 146 over 336. So again, the numerator is 3 times the first denominator plus the third denominator, or the first denominator times the third denominator, so 6 times 8 plus 2. Well, 6 times 8 is going to give us 48. 48 times 3 is going to give us 144. 144 plus 2 gives us 146. And then 6 times 7 times 8 gives us 336. So his observation also works for the second example. Problem is if you just prove it for these examples, it may not work for all the numbers. So you have to make a general case. That's what this question is asking. I just wanted to kind of go over this first so you understand what's going on, what's trying to be proven here. So how are we going to prove this for a general case? Well, what we want to do is instead of using actual numbers, we want to use variables that can be any number. So what we can do is we can let n plus 1, and n plus 2 be 3 consecutive numbers. Right? That's how you take 3 consecutive numbers and write them generally as variables. n plus 1, n plus 2. So instead of writing 3, 4, 5, n plus 1, n plus 2. And it always works out because if n is 3, 3 plus 1 is 4, 3 plus 2 is 5. If n is 6, 6 plus 1 is 7, 6 plus 2 is 8. So 3 general consecutive numbers. So what we want to do now is we want to add the reciprocals of these 3 consecutive general numbers. So 1 over n plus 1 over n plus 1 plus 1 over n plus 2. We have to see what we would get. And actually, what do we want to get? We want to get 3, this pattern that we observe, so 3 times the first denominator times the third denominator. So 3 times n plus 2 plus 2. And then the denominator here would just be all of these multiplied together, n plus 1, n plus 2. And this actually simplifies here. So this would be 3n squared plus, so this would be 3n. 3 times n is just 3n. And then when you distribute that inside the bracket, we'd have 3n squared plus 6n. So we'd have 3n squared plus 6n plus 2. So we basically have to prove that this is equal to that. Right? So let's work with this left side here. Notice we are adding 3 rational expressions. So we got to get a common denominator for these. So n times n plus 1 times n plus 2 would be the common denominator. Right? All these factors are different. What do we have to multiply this n by to get this lowest common denominator? Well, we got to multiply it by n plus 1, n plus 2, which means we have to multiply the top by n plus 1 and n plus 2. This here, we have to multiply by n and n plus 2 to get this. So we got to multiply this 1 here by n plus 2. This we have to multiply by n and n plus 1. That's what's missing to get this. Meaning the top we have to multiply by n plus 1. Right? So 1 times n plus 1 times n plus 2, you can actually FOIL those two brackets out. So that would be n squared plus 3n plus 2. You'd have 2n plus n. That simplifies to 3n. N times n plus 2, that would give us n squared plus 2n. And then over here, we'd have n squared plus n after we expand everything. Right? So I kind of skipped a step in showing these. I showed it up here, just trying to save room. But yeah, from here, you just simplify. So continuing this, let's continue it over here. Let's simplify these like terms. So n squared plus n squared plus n squared, what does that give us? That gives us 3n squared, right? So those go away. 3n plus 2n plus n, those are all like terms. That gives us 6n. And then we're just left with this 2 here. All over n plus 1, n plus 2. So notice we took that left side and showed that it equals that. And so what we can do is we can now generalize this and say that Sam is correct. Right? And again, another way to show this, we could take out the 3, we could take out the n, and we could rewrite this as n plus, why am I getting confused now? Oh, n plus 2, yeah, and then plus 2. And you know what? It might be better to actually show it like this. So maybe it's better that I didn't even expand here. Just because it relates then better to the question. You can expand. We showed that the expanded version's equal. But you may want to show that this is equal to that. Because it actually shows that you're taking 3, you're multiplying it by that first denominator, times that third denominator, and then you're adding 2, right? That 2 there. And then here, you're taking all 3 denominators, multiplying them together. But either way, whether you expand it here and show that the expanded versions are the same, or you leave it like this, you take this expanded version and factor it, take out a 3n to show it like this, either way you show that both sides are the same, and so you proved it, right? And so basically Sam's conclusion works for all cases, and you could test it out. You can take you know, any consecutive numbers. You could take large numbers even. You could take 1 over 100 plus 1 over 101 plus 1 over 102. And that's going to give you some kind of fraction. And you can test this here. So you could take, the numerator would be 3 times the product of the first denominator, 100, times the third denominator 102 plus that 2 at the end. That's going to be all over all three denominators multiplied. So 100 times 101 times 102, you're going to get a big fraction, and then it'll probably simplify. And then if you threw this through that same set of fractions, set of sum of fractions into your calculator, 1 over 100 plus 1 over 101 plus 1 over 102, it would probably simplify to the same thing, right? Anyway, tough question. It was a tough question to explain. I was kind of jumping around a little bit, actually tripping over my own words. But yeah, because we proved that both of these sides equal, or that we showed for a general case that the numerator is 3 times the first denominator times the second or the third denominator plus 2 all over the three denominators multiplied by each other, we proved that Sam's conclusion is correct.